To deliver broadband internet from space, you must maintain a continuous data link with a target moving at 27,000 kilometers per hour. You need a continuous line of sight from the ground to a target in low Earth orbit at 550 kilometers. You must hold this connection while pushing gigabits of data, keeping latency under 20 milliseconds. Traditional satellite dishes use physical motors to point a parabolic reflector. Mechanical gears are too slow and prone to wear to continuously sweep across the sky, tracking targets at these orbital velocities. The modern hardware solution eliminates physical movement entirely, utilizing a strictly solid-state, flat-panel architecture. To solve the orbital tracking problem, engineers replaced mechanical motion with computational wave physics. To see how this is achieved, we have to look past the exterior casing to the internal macroscopic layout. This exploded view isolates a massive 6-layer printed circuit board. This laminated structure acts as the terminal's brain, housing control chips and copper pathways. Buried within is a highly precise arrangement, a hexagonal honeycomb grid composed of exactly 1,280 separate copper nodes. This static copper grid is a phased array. It is the physical mechanism used to steer a concentrated radio beam without any moving parts. This diagram shows a cross-section of a single antenna element. A copper wire, known as a microstrip transmission line, runs from a control chip and terminates directly beneath the circular copper patch. The terminal sends a 12 GHz alternating current through this wire. This means the voltage flips between positive and negative once every 83 picoseconds. When the voltage cycle reaches its negative peak, electrons crowd the tip of the feed wire. This concentration repels the free electrons in the overhead copper patch, shoving them to the far side and creating a severe charge disparity. Because one edge of the patch is now positive and the other is negative, the metal generates horizontal fringing electric fields across its surface. At the exact same time, the physical flow of those electrons generates a magnetic field. These magnetic vectors sit perfectly perpendicular to the electric fields. By oscillating these two orthogonal fields billions of times a second, the energy propagates outward into space as an expanding electromagnetic wave. A single stationary copper patch converts high-frequency electrical current into an expanding radio bubble, serving as the foundational building block for beamforming. A single antenna patch yields an omnidirectional signal that is too weak to reach orbit. This diagram models wave mechanics by placing two adjacent antennas next to each other and feeding them the same 12 GHz signal simultaneously. As the waves expand, they collide. Where two wave peaks perfectly overlap, they double their amplitude. This is constructive interference. Where a peak and a trough collide, they cancel each other out in destructive interference. When we fire all 1,280 elements simultaneously, the overlapping ripples coalesce into a single tightly focused beamfront. Aligning these 1,280 weak waves mathematically synthesizes a directional main lobe that is roughly 3,500 times more powerful than a single element. The array now produces a beam powerful enough to reach space, but firing all patches at the identical moment shoots that beam straight up, perpendicular to the board. This profile demonstrates wave phase, the specific degree alignment of a wave cycle from 0 to 359 degrees. By shifting the timing of the cycle, we create a phase delay. To steer the beam, the system applies highly specific, sequential phase delays to the signal across the adjacent columns of antennas. Because antennas on one side emit their peaks slightly later than the ones opposite to them, the resulting plane of constructive interference forms at an angle. Sequentially delaying the emission physically tilts the beam. Dynamically altering these delay patterns allows the static array to sweep its main beam anywhere across a 100-degree field of view. Managing this complex delay architecture requires 20 dedicated beamformer microchips physically mounted on the circuit board. These chips use the terminal's GPS coordinates and known satellite orbital data to calculate the exact spatial geometry required for the link. These phase shift calculations for all 1,280 antennas are fully executed and refreshed every few microseconds. Microsecond delays in electrical signals effectively steer a radio beam faster than any physical motor. Directing the wave is only half the problem. The terminal must still embed massive amounts of binary data within it. It accomplishes this using a protocol called quadrature amplitude modulation, or CAM. This method transmits digital data by varying two distinct properties of the carrier wave at the same time. First, the system modulates the amplitude, altering the height of the carrier wave to represent different data states. This diagram tracks the 12 GHz signal. While varying the height, the system simultaneously modulates the phase, shifting the horizontal alignment of that same wave. This polar coordinate grade maps out the standard's density. By utilizing exactly 64 unique permutations of combined amplitude and phase, the system operates on 64 QAM. Each coordinate on the grid represents a specific 6-bit binary sequence. As the wave changes its amplitude and phase to match these coordinates, it physically encodes the data. The transmitting chips generate a totally new symbol permutation every 10 nanoseconds. This ultra-fast modulation packs up to 540 million bits of raw data per second into the steered carrier beam. There is one final operational limitation. The physical array cannot transmit a high-power beam and receive a faint signal from orbit at the same time. To manage this, engineers use time division duplexing. This rapidly toggles the entire board back and forth between exclusively transmitting and exclusively receiving modes. This diagram visualizes a 1-second timeline. Roughly 74 milliseconds of every second are dedicated to upload bursts, with the remaining 926 milliseconds reserved for download bursts. These millisecond-scale blocks are distributed evenly throughout the second to maintain the low latency required for real-time web applications. By bridging the scale of orbital mechanics with the picosecond precision of wave physics, this solid-state system tracks its target without a single moving part, relying instead on the nanosecond scale synchronization of 1,280 stationary antennas.